We will now start with our second keynote speaker, who is Professor Harald Sack from the FILS Karlsruhe Leibniz Institute for Information Infrastructure, and he is also a professor at Karlsruhe Institute for Technology. Sorry. Harald is professor in Information Services Engineering and Information Infrastructure. And you will talk about the sources C apprentice, or why the semantics still matter, and we should not only trust in machine learning.
Possibility to speak here to you, and the title of my talk is The Sorcerer's Apprentice, and SM for deep neural networks was invented, and everybody thought by that time in the late 80s, neural networks will soon solve everything. So did my supervisor. So the topic that I had was stock predictions with backpropagation networks. And since I'm not cruising on my yacht and being insanely rich, you see that this not really worked out well. So therefore still first doubts were raised, in my opinion, so I left the topic. So what I did next in my PhD was then theoretical computer science. I thought I had to do something more sound and solid. I was working in formal verification, and then I turned to web technologies, and then I ended up in semantic web technologies, which still then, I was able to close the circle again to artificial intelligence. So, yeah. Why does also today artificial intelligence and also machine learning seems to have something magical? Probably you know that quote here: any sufficiently advanced technology is indistinguishable from magic. So this is a famous quote by Arthur C. Clarke. You might know that author and one and other films or novels. So people soon tend to overestimate a technology that they not really understand. Sometimes this is justified, sometimes not. Here. On that here, but I can tell you it's really, really difficult, but nevertheless, Google AI is able to detect breast cancer much better than humans. So for visual classification and visual computing tasks here, today, artificial neural networks perform much better than humans do, if they are trained in a rather specialized niche that you can see here. So this means if they are better than humans, then probably they are also better than humans in other topics, but beware. Then you see sometimes headlines like that. So he was titling AlphaGo, which is of course a bit of exaggerating. Of course, it took 40 days to train exactly that kind of artificial intelligence, but of course it's able to do and perform much better than a human in this tiny world of Go, but of course not in everything which here pertains to human knowledge. However, probably you also saw this last year. Artificial intelligence now is also creating art, and this art for sure has some value. So this piece of art was sold for more than 400,000 American dollars last year, and this might be only the beginning. So artificial intelligence is not only able to play strategic games, it's also able to create something, and also to at least create something similar like art. Great the power of these technologies, and even the experts make intelligence of an average human being. And we all know that this did also thanks to that. Let's get a bit deeper into the topic. Where does this kind of magic come from? Okay, so we go into a rather brief and short history of machine learning. All started cells, of the neurons, how they fire and activate each other. But of course, this is only a structural or a functional model and not really explains how really intelligence can be devised. And only a few years later here, Warren Sturgis McCulloch and Walter Pitts, they came up with a mathematical formalization of exactly that kind of biological process. So the neural cells in our brain do. Some remarks on the side. So of 12, Walter Pitts was reading Principia Mathematica from Bertrand Russell and Alfred North Whitehead. And he had some doubts about something, and he wrote a letter to Bertrand Russell, which Bertrand Russell read. And of course, Bertrand Russell did not know the age of that guy, and he invited him to research together with him, which was not possible for Walter Pitts being 12 years old. So this was really an extremely interesting guy. Okay, and he came up exactly with that kind of cell. And the purpose why they did this, they wanted to show to perform Turing computable computations, and they did, because it was able to mimic, let's say, basic logic functions, which in the end are Turing computable. So they managed to do that. One step further, how, this was the next big question, such a small cell could be able to put in a feedback loop, which was able then to adapt these input weights that in the end form the decision, or the let's say the basics of the decision of this weighted sum function that you see here, that decides whether exactly here the neuron will fire or not. So Rosenblatt did this, and already in 57, 58 they were able, based with this perceptron algorithm, to build the first neural network that was able to do visual computing. So this thing, the Mark I perceptron, was able to distinguish numbers or recognize numbers, digits, from 0 to 9. So this was a great piece of history. It was not an electronic computer, it was working electromechanical, which means there were small electrical engines which in the end were able to switch these small little potentiometers which represented the weights of the neurons. So this was a really great piece of technology. Okay, so you see here, I did not also include the hype cycle in there for artificial intelligence, but the heydays or the great times of artificial intelligence were here. The red ones, which is the so-called golden age between the 1960s and 1970s, since in the beginning they had really tremendous progress with this, recognizing numbers and stuff like that. But already in just now, he found out, together with his colleague Simon Peppard, that a neural network, a perceptron, is only able to do a so-called linear classification. So it's not able to do something which is a quadratic or a polynomial kind of decision problem. To solve this was more or less clear. We need more layers in a network like that, but there it was unclear how then the learning or the adaptation of the weights should propagate backwards. And this was then in 86 when Rummelhardt and his colleagues came up with a backpropagation algorithm, and then there was the second heyday. But between that time, you see that blue period, this was the dark age or the winter of AI. And then between the late 90s and 2000 come of that. So people did lots of experiments. So they trained their network, and then they tried to do several classification stuff. So for example, can I classify a baseball? Can I classify animal faces? Can I classify clouds or buildings? And sometimes it's not really clear, if you look into what the network really sees, what it does. So for example, is it really a cloud what it sees, or does it simply react to the fluffiness? Or with the buildings, it's quite clear, because often in the buildings, they don't see the structure, but probably the sky. So we had a case, so this is also several years ago, when we also tried to find out what are the key parts of a picture that are responsible for the classification of a network. And we found out, so we could very well do classification of airplanes, but only of airplanes which were in the sky. Simply because the network was training with lots of pictures of airplanes, but not airplanes on the ground, airplanes in the sky. And it's of course much easier to make a categorization or classification. If you try to find out, or if you try to identify a huge, let's say a vast area of a single color, then let's say the technical details of an airplane. So with the type of pictures, or let's say the training set that you are using, you are, of course, we know this already, you are biasing somehow also your network. And in case, you know, you have some flaws in your training set, these flaws, of course, will also be in your network. And there might things you might not have considered. So therefore, then you will see, if you are lucky in some cases, then misclassifications when it turns out exactly you have a picture that was not represented in your training set, and your training set contained a kind of bias. So this happens. But also with knowledge graphs, you might have some problems. They are, of course, in another way difficult to solve. So for example, so here it's the problem, either you go into detail, you try to cover up, let's say, a specific niche area in its completeness and to the lowest level that is necessary for your application, or technology which contains, you know, knowledge about the entire world. To put everything together, to create a knowledge graph about the entire world in a rather deep and sophisticated, let's say, and particularly granular level, this is next to impossible, because you have, you know, to model the exact, let's say, image of the entire world, with, of course, all our assumptions about the world. And this, of course, are two sides of the same coin. So either you go into local details, or you go for completeness or global coverage. The question is, how can we solve that? So up to now, I don't give you the answer, but of course, magic, to come back to exactly that point, 90% of most magic merely consists of knowing one extra fact. This means if we had known this before, probably we wouldn't think that it's magic, but somebody who knows this extra fact is able to perform something which we think might be something like magic. I will show you again an example of one of these GANs, of these generative adversarial networks. There, what was done is you get a description here of a bird, and the network was able then to create images of these birds. These images were not somehow in a database, and the bird that contains exactly these were generated in the way, you know, we have seen just when I explained what is a generative adversarial networks. And it's quite impressive. So, for example, when you said, this is a small light gray bird with a small head and green crown nape and some green coloring on its wings, you almost get a bird, because I forgot to describe that it also has a beak. Okay, so you have to describe it in its entirety, then the network exactly knows what to do. And this is nice and quite a bird really exists or not. So, some guy had the idea, okay, so this is working especially only for birds because it was trained for birds and it has impressive performance. Why not taking into account ImageNet, where we have images about everything, and use this as a training basis? And we also have descriptions of ImageNet. So what is on the picture? All these pictures have descriptions. And he did this, and he used something more general, which means he used ImageNet exactly for that same technology. Which means now you are able, with that pre-trained network, to give it some textual description, and the network then generates a picture for that. You can also try this out. I have provided you the link for that. So, a flock of sheep on green meadows. Yeah, comes close, doesn't it? So, looks not so bad. So, I tried out, let's say, something. So, as we see, there might be pieces of some girl on that picture, but the network not necessarily know how to exactly combine them. And for example, how many eyes, how many noses, how many whatever I should put in there. So this is kind of knowledge which this network did not learn so far. Then I thought to myself, okay, give a better description, see what happens there. A girl with 2 blue eyes, 1 upturned nose and a red mouth. Yeah, there's red in the picture, and yeah, it looks a bit scary, doesn't it? So the point is there is a lot of knowledge missing. And if we assume that, this network works very well in the niche application area with a bird, and then you think, oh, let's use it for something different, then it's not necessarily possible that exactly this might also work in a more general setting, as we see here. The other thing where it works very well is, for example, if you want to create something surrealistic like melting clocks over the desert. So this is a great picture, I think. So therefore, try it out. It's really nice. So it makes great album covers, for example. So this is really perfect for that. Yeah, now the question is, where does all of this lead us? So where will artificial intelligence go? And what would be the goal? We have seen over the last few years where exactly these two types of artificial intelligence, machine learning and knowledge graphs, come closer and closer. So we are using deep learning technologies for knowledge graphs. So for example, we are using NLP and knowledge extraction via deep learning to populate and to extend existing knowledge graphs. So we do this with Wikidata, we do this with DBpedia and stuff like that. And we are also using these technologies for ontology learning and to extend and to refine knowledge graphs based on that. And also for ontology alignment, link discovery, and for the integration. So this is ontology or knowledge graph alignment. If we want to integrate two knowledge graphs, then we also have to do ontology alignment for that. And this also is supported nowadays by deep learning technologies. But this is only one direction. So quick example. So what they do in Wikipedia, for example, is they are using NLP technology for simply finding out, okay, we are transferring exactly this kind of structural knowledge into RDF, or we are reading a sentence like this one, and we can easily create here RDF triples out of a sentence like that. So this is already happening. This works quite well. It also works in the other direction. So knowledge graphs for deep learning. So what we do here, for example, we have one kind of knowledge representation, knowledge graphs, where everything is explicit. We have the entities there, we have relations there, we have a ontology which is somewhere in the back. And what you can do is you can simply put all that kind of knowledge or try to put it in a more latent semantic representation. So you can, for example, put let's say the graph that is constituting the knowledge graph into a vector space while preserving its semantic properties. That vector space then has the particular property that neighbored vectors have a semantic similarity, which is quite handy if you do this for knowledge graphs. Of course, this is rather difficult and also has a scalability problem. And the question is then, how do I exactly map the environment or the surrounding of another kind of embeddings can not only create it for element basis. Then you have, again, vector spaces, keeping the semantics for exactly the entities that are represented in there. But the problem is these different vector spaces are not necessarily easily combined. If you simply, for example, concatenate these vectors, in the end, you don't preserve the semantic similarity issue. So therefore, combining exactly these latent semantic representations into a common hybrid embedding while preserving exactly these semantic properties, this is something future goal in the research. There's something promising which is called graph convolutional neural networks, which exactly is the same. So you're trying to transform a graph into a vector space while keeping all of its properties. But one of not only related with each other because they have not only an edge weight, of course, they have an edge property, and also the properties are related with each other. So we have first to find what's the best kind of representative that it's really also contained completely in the knowledge graph. Before doing so, we are, for example, using different kind of entity and entity category networks that are extracted from knowledge graphs to do a so-called dataless classification, which means we can do classification without a training set. And this is simply based on semantic similarity of the content. And we showed if we do this on short text and do a classification there, we can achieve almost as good results as you can do as if you have a large training set. And we are applying this kind of technology now for the classification of archival documents, for example, for the German National Archive. But where will technology go to? So one way to integrate here semantics and this connectivist representation of neural networks is the so-called neurosymbolic integration, where they try to combine different neural networks together with symbolic representation in a specific way, that you have a hierarchical layer ensemble of networks which are interconnected among each other, and where you have specialization and generalization between the people are working on that, but so far there are I can't say that are not promising results, but this is not as far as it should be. Let's put it that way. And it's not clear whether this in the end will turn out in the way like their inventors really hope it will. But let's see. So this is first, or one of the, let's say, starting points where they start to integrate these latent semantic representations and explicit symbolic representation. As a short take-home message for you, short-term goals for knowledge graphs could be simply coming from these two competing efforts, where on the one hand you go into detail and on the other hand you try to go for completeness. Don't try to make everything explicit. Also work with aggregations, or work with things which are not explicitly given there, which are somehow implicitly there, and you can somehow restore them, no matter how. And for deep learning, this is even much more important. For deep learning, try to make the implicit, so what is in this network of nodes stored, what are the weights, try to make these weights in some way explicit. Otherwise, to end with a movie quote, all those moments will be lost in time, like tears in the rain. It means you have a network, the network is damaged somehow, or you have to retrain it, you have no idea what was in there, and all the knowledge that is in the network will be lost. Thank you very much for your attention.
Thanks a lot, Harald.
Please permit me one last sentence. I want to advertise one conference in September this year. So in Karlsruhe, we are organizing Semantics 2019, the power of AI and knowledge graph. And I would like to welcome you in Karlsruhe in September. So there's a website, 2019semantics.cc. Exactly. And the deadline has been extended, so you still have a chance to submit to the research innovation track. It's 13th of May is the deadline.
Thanks a lot, Harald. Do we have one question? Yes.
I'm worried about moose because my wife was almost killed while driving into one. So as a note to the Volvo people. And I'm thinking that there are, even though that event is very rare, there are millions of possible events that could kill you. So by connecting that to a knowledge graph, could we somehow address that and connect the physics to that kind of situations to deal with those very rare events?
What do you expect as an answer? Possibly. So I can only tell you I don't know. So possibly yes. Let's see. Sorry.
Right. Okay, thanks a lot, Harald. So, with Meta Solution, and I welcome up on stage Matthias Palmer and Althea Hayes.
Okay. Hear me now? Yes. So I want to be able to see the same thing as you see. Okay. So, this talk is going to be a little bit different. It's not going to be so much about AI, but more about the knowledge graph part. Because in this case, I'm going to present how we have been working with a customer, the Public Art Agency of Sweden, to expose their information as linked data. So the challenges they had, so they had an old database, which was of course not perfectly maintained, and the information model was weak at best. They want to be able to maintain their own design and change it and have a design bureau database, but maybe not in one go, because they may want to stick with that for some more time. And they also wanted to move towards linked data because they are in the cultural heritage sector, which is moving towards this area in Sweden, and I think in many areas as well. And they had also learned that according to Swedish law and European law, and because it's a good thing, they should expose information as open data. And linked data is, of course, open data. So here is the result, a peek. I'm going to give you a demo a bit later. So the result is that we have over 300 pieces of art, 1,600 pictures. It's searchable in a nice UI on their own web page. And it's just the start. So I'm going to tell you a little bit how we came to this point by starting with the architecture. The architecture. So in this view, the source was that we got from the old database in CSV, and we needed to write some import script. We have our triple store, layers on top of the triple store, giving us access control, Solr indexing, and a lot of exciting things. And we have an administrative UI, which will be possible to use later if they will decide to ditch this part. And then we provide a simple linked data view, as well as embeddable search interface in their own WordPress page website. And these are driven by our library RDF Forms, which has kind of a templates or application profiles. We'll tell you a little bit about that. And then Entryscape blocks, also tell you about that. And we can also generate a specification from these templates. And we hope that all these pieces will make it easier to take into account new customers as well. And even all our technologies are open source, so we're seeing that this could perhaps be used by others as well. So I'm going to tell you first a little bit about RDF form templates. So we have seen the need from a long time ago already that just using RDF and linked data is kind of hard, and you need to make it easier for the based editor to show that. Here is a very simple snippet of saying that, okay, we need to say that a piece of public art is either indoors or outdoors. And of course, we can describe that using RDF schema or OWL or whatever shows Shackle or Shex. We have heard some of these options, but none of these technologies are really aiming for all these things to both generate editors, presentations, specifications, and validations. They are typically rather to specification and validation. The next part is the Entryscape blocks component. And what we realized that, okay, we can build a web application where we can show off the information that people have provided, either in the UI or we have imported it through scripts. But sooner or later, we are going to have people that want to know, I want it to look completely different. I don't want to see this only in the application here. I want to see this as part of my website, or in this specific case. So what we are aiming for is to do more data-driven websites, where the data-driven part is linked data, and it does not require a lot of development effort for every time you need to do that. So what we did is that we developed a library, a JavaScript library, allowing you to annotate parts of the HTML or short codes, and a few of you may have heard this because I've talked about this previously. But these blocks is like, okay, how to provide a link, a filter for a search, a facet, a list, a piece of text, etc. All of these blocks, you can sprinkle them across your environment, and yeah, you get your UI. Of course, we can't solve all tasks, but the tasks we have aimed for are to search for linked data entities, to display in linked data entities. You can also display multiple linked data entities in one page, which are interconnected, so you start with one and it will figure out by following relations. The limitation is that linked data in itself, even though a web architecture using the web, the links and everything, it's somehow not enough always. Sometimes you need to be able to do clever searches. For instance, if you don't want to do faceted search, it's not something you can get out of plain HTTP. You need to have an API on top of that. And of course, you could use Sparkle, but Sparkle is not perfect when it comes to free text searches and facets and stuff like that. So in this case, we are relying on Enterscape's API, which provides a few additional things here. Otherwise, except from that, blocks is rather a generic piece of technology that could, in principle, be called linked data blocks. So, diving back into the data model we defined for the public art agency. In this case, we defined 5 entities: the work of art, the connected artist, there is an address, a property unit, and an image, or several images. Exactly which properties we have on each, well, there are too many to go through them, but a few of them, many of them are from Dublin Core, Friend of a Friend, schema.org. There's something called cadastral vocabulary for describing more properties, and for a few we didn't find any existing schemas, so we have to invent a few own, and we did that, of course, for this project. So the script import. So right now we are doing this import by having custom conversions. No strangeness there, but the challenge and this is not a unique challenge to this project. When you have information that is not perfectly modeled and there isn't any identifiers there you can use, it's hard to generate stable identifiers from this. So until we get to a point where they ditch the old system, it's going to be a bit, well, not perfect when it comes to identifiers, to having things state, oh, the building has a new address. And of course, then how we have identified the building before will change. The goal is here to rely on CSV on the web. Has something called table annotations, allowing you to describe how a CSV expression actually corresponds to a linked data expression. It's also used for actually telling you exactly which columns are in the CSV and what kind of, if they are integers or floating points, etc. But it can also be a link over to linked data. So to go over to that would allow us to ditch the first step to write custom conversion scripts. So a demo. Let's see here. So here is Enterscape, and here we have, let's see, there's imports. So let's look at the last import. Here we have work of art, and here if I look for Underlandet, I get the metadata according to RDF form template that we specified for the work of art, and so on. We have, click on the same one again. And here if you want to look at, okay, who was Barbro Hedström, you can click, and then you follow the link, so to speak. Here you can also see that there is a link up here, and if I click on that, that's the step 2 demo. This is a standalone outside of the application, and now this one is driven by by 2 things. It's driven by a very simple block, an Enterscape block, which basically, well, actually 2 blocks. One block which has a small template that generates links to the actual direct RDF formats to download, and another one that uses the RDF form template to generate the full metadata for this type of entity. So that was 2 pieces of the user interface we generated. Let's take this one before we go to the really nice one. This is the specification. It's generated from the template. So the same template we wrote for just being able to show it and edit it inside of the application. Actually, I didn't show you that, but here you can do edit, and then you get an editor with various levels of metadata that you can fill in. You can add another decade. Well, doesn't make sense, but yeah, I won't say. So the same template is used to generate a specification, looking kind of nice. And then finally, we have the UI embedded into the public art agency. So if you are interested, it's mobile friendly. You can go to it on your mobile phone, statenskonstråd.se. And here we have several things. It's possible to search for all these pieces of art. Here you see card-based layout of the art, and you can filter like by clicking on the facets here. I'm sorry, everything is in Swedish. That's how it is. The data was provided in Swedish as well. So if I filter on here, I get only those. And if I want to search, I can here maybe search for some, I don't know what I should search for. Helena, apparently there is a Helena here. No, I did something wrong.
Hi, can you hear me? Yep.
Thank you. Okay, why is that not appearing?
Just as we're getting set up, and he's badged today, but yesterday he was wearing his proud EU and British badge. So we're over Brexit, aren't we? I think.
Well,
yes.
We're hoping we're over it, but
Yeah.
fingers crossed for everybody in the room, and myself included.
I'm Peter Voisey. I work at Findwise. I'm a consultant and project manager, and over the past year, we've been working together collaboratively on a project to create a new learning hub that Richard is going to talk about, and perhaps also explain about how
0.5 million people that we have to make sure that we gave people the best possible training, which ultimately is the best possible care. So one of the things that we're trying to tackle at the moment is the changing way in which people learn, and the multiple sort of different modalities of learning that are currently available, and how familiar.
soft in an AI. So less than 50. And how many of you have used knowledge graphs before? Again, about 50. Okay. In terms of AI, we all know that we need. Thanks. We need clean, structured data, and so if we were to say this was somebody's organizational data, as it were, how much do you think in terms of structured data is going to be represented here? Well, it turns out that only about 20% of our data on average across organizations is structured, 80% being unstructured. So how much in terms of structuring are we doing to that 80%? Well, it turns out that it's less than 1% in terms of we're actually only using 1% of unstructured data, or in fact evaluating in terms of analytics. And then one other interesting fact also in terms of, if you're looking at analysts, 80% of their time is actually used just to find and prepare data before the analysis.
So I'm going to talk about one of the solutions that we've come up with to how to make the learning content that we've got available, much of which is e-learning, how we make that available to our users. So we've come up with this concept of what we're calling a learning hub, content of learning data more, and making that available to our learners in the best possible way so that they can easily find what they need. There's a great story I had with a consultant at Great Ormond Street Hospital, which is a world famous children's hospital in the UK. In London, explaining what he's about to do to a child onto the operating theatre to that child, and sometimes he struggles with that. So he was very candid with me, very open, and said, I have a YouTube video that I go to that helps me remember how I'm going to explain that to the parents before I do their operation. And he always struggled to find that. So one of the solutions is for us to make content like that available to him, to his peers, and to the community, so that everybody can benefit from that knowledge, that expertise. But that obviously comes with some challenges, as you might expect. A lot of the data is sort of largely unstructured. I would say, well, using Peter's 80-20 rule, I would say about 80% of the data we've got is very poorly structured and very poor metadata, if there's any metadata at all. I got my wrist slapped yesterday for daring to say that one of our systems uses completely crowdsourced data. There's no pick list, no structure at all, which in the semantic world is a big taboo. So these are some of the big challenges we've got. So how do learners want to benefit from? We've also got multiple systems. A conservative estimate is we've got about 150 different learning systems within our organisation. The reality is I suspect it's probably much higher than that, but they're the ones we know about. So how do we make all of those systems interoperable? How do we make sure that the content that sits on these silos is all interoperable? And again, that's something that we're hoping to tackle with this new product. And then finally, we're sort of noticing that people are learning in different ways. So the way that they traditionally learned was they were given information, but increasingly people are going about seeking the information themselves. So they need to be able to find that, and they need to know that it's quality assured, and that it sort of meets their demands in terms of the way that they learn in a much more informal way, rather than in that very formal, structured way that they perhaps learnt in higher education. So I'm going to pass over to Peter just to give an overview of what knowledge graphs are, given not everybody is familiar with them.
As Ratnesh mentioned or alluded to, this morning, it's largely made up of a taxonomy and ontology, and Google uses this in their back end. They've done lots and lots of hard work to get there. In the case of HEE, we're using a knowledge graph based on RDF. One of the smart things that is available these days is the standard of tools and how usable they are. In terms of the underlying semantic web technologies are actually hidden from the user, and so this makes it more easy really for the knowledge engineer and the knowledge expert to get their hand on these tools and create taxonomies and ontology. Now, a knowledge graph or graphs change the way we traditionally look at data. So the first point I wanted to make is around polyhierarchy. When we traditionally look at taxonomies, we're looking very much in 2D tree type taxonomy, whereby a concept could only used to be appearing once within the hierarchy. But now, of course, because we're looking at a graph format, say, for example, here, the example here, sciatica, that can appear more than once throughout the hierarchy. And this has big implications in terms of how a user can navigate to content. You can have different perspectives, or different users with different perspectives, and they can hit the same topic by going through different paths. The other thing I wanted to mention, obviously, synonyms and acronyms aren't new at all, but again, the tools that we're using today kind of formalize the process in terms of when you're creating a taxonomy, you can automatically think about the different ways. And then the final point that I wanted to make in terms of ontology, we see these really as the business rules, and in terms of creating an ontology, often starting off looking at the classes and creating the main relationships between those classes. And this indicates not only how the data is driven, but it should reflect in terms of what's important. Whoops, thanks. What's important in terms of what runs the business, and so your data automatically follows that.
So in practical terms, going back to the previous speaker, I think these are actually really beautiful. I think these are works of art almost in themselves. What we're looking at is a 360 perspective on that information. So if we tag an e-learning resource, for example, with the term sciatica, that branches off and relates to all of the different classes of words that are associated with that. So potentially the symptoms, potentially the treatments for that, the body structures, the body parts and things that are all associated with that, the professionals that might be involved with that. So you suddenly get this sort of 360 perspective on that like Wikipedia. Something catches your eye and it takes you. We've tried to create this really rich knowledge graph that allows you to explore concepts, explore all the different areas around it. So every time that you click on a new term within that inline text, it regenerates that part of the knowledge graph and takes you to a different perspective. So Peter's going to explain a little bit about how we actually structure that, how that works in a practical level within our organisation.
The prototype that we've put together, I can demo this to somebody if they're interested later on. Otherwise, just contact either me or Richard, and I can take you through a demo. So essentially, we're using two main platforms. We're using the FindWise i3 platform to ingest the different types of data, give this data structure and enrich it. And during this process, we're also relating this to the knowledge graph, which we're using currently Pool Party to create the knowledge graph. So we're taking concepts that are in the knowledge graph and annotating the content accordingly. So a simpler view may be something like this. The machine, in effect, is reading the term sciatica, referring it to the knowledge graph, being able to annotate it. We'll look at the content itself, give it some kind of aboutness score, and in terms of it, we'll also notice the relationships and the related concepts to sciatica, and be able to exploit that in the user interface. So what are the game changers for me really are the new tools. They're very user-friendly, and like I say, it means that the knowledge experts, knowledge engineers can have access to the tool to be able to create and make knowledge explicit. In doing so, they're unwittingly codifying knowledge, and they don't have to worry so much about the underlying semantic web technologies. Secondly, these tools are collaborative these days, which is very important. One of the things that we find difficult in terms of approaching organizations once we're doing the project is the difficulty of maintaining that project in terms of information governance. Because these tools are collaborative, almost the tools provide some kind of framework for them. And lastly, automatic and semantic. This almost gives organizations a second chance in terms of actually organizing their data in a very quick and effective way. So Richard will stack what we've done in terms of the prototype up against AI.
Yeah, so we've not really touched a huge amount on the use of AI, but actually what we're doing is essentially using a sort of very narrow focused, a very weak AI or very weak machine learning to analyze that corpus of text or analyze that corpus of resources that we're pointing at it, and give it some semantic meaning, some classifications, some and make some sense of that data, and give it some structure where there is no metadata currently. Currently, that's a very manual process. That's something my colleague in the back there, Emily, and I have the dubious honour of doing on a regular daily basis. But actually, the AI is becoming better and better at doing this. And it's probably not at the same level as a human at the moment, but certainly if you think about image interpretation and things like that, it's getting to the point where it's becoming much more realistic and in taking some of that human burden away from us and moving into this sort of stronger AI space on the model. And I don't think any of us can say that's a bad thing, because the last thing we want to be doing is classifying data all day.
Thank you.
So, tack, thank you.
Thanks a lot, Richard and Peter. Do we have for Peter and Richard? Yes, we have a question over there, Eric.
Thank you for the nice talk. I was thinking about you connecting all these things together into a big 360 picture of some concept. You had some different colors there in the ground. Have also some way of separating these different perspectives that you have in there. I guess like the patient perspective and keeping track of what belongs to what kind of context or whose perspective. Right.
So currently the prototype is going to be used for doctors and nurses rather than patients. So we're taking that language is being overlapped at the moment. So in terms of the different colours, they would be looking through the taxonomy, giving certain and diseases or anatomy. So that was how that was reflected in the chart.
Any other question?
At the front.
Yes, we have over here.
Actually, can you can you get to that 360 screen, the graphic? Because I had a similar question. You had a bunch of lines. Let's see. Okay, there we go. What are the meanings of the lines? What is the meaning of the blue line between heat ice and SCASE? Yeah.
Okay, so in terms of the relationships, currently while we're setting up the taxonomy and the ontology, we're using relationship related to. But obviously in the ontology, we also within the tool have the ability to define our own relationships, specific. So they really here is more of an illustration of what could be. So like I say, the ontology at the moment is based on very simple related concepts.
Okay, thank you.
So yeah, just looking at the colours, this is a visual representation rather than perhaps an accurate portrayal, but the green section, for instance, are the symptoms that are associated with that. The yellow section is perhaps the some of the complications that happen as a result of that. The red is the body parts, the blue is the treatments, those kind of things. So they're classes of words that we can associate with them. We're having a
Thanks a lot. Anna Svensson from SweLife, and Hannah will tip on AI. Already, the stage is yours.
Fredrik kom in. Är micken på? Nej. Så, nu.
Ja, men batteriet är för lågt. Vi tar och byter.
Ja, det är en massa fusk. Okay, I will start while Fredrik is opening the presentation in the correct way. So I will give you a talk about the patient's perspective on AI. So we will stay in the healthcare sector. I think this day has been very wide, so I have a bit of trouble putting myself into this puzzle. But I will talk a little bit about data and not AI. And it's only related to care and healthcare. Jaha, men om börjar med den första bilden. So, do you remember what you ate for breakfast or when you were doing your last exercise? Maybe, maybe not. This is one of the questions that you often get when you go to the doctor as a patient. The dots there that looks like the ends of war, Myrornas krig, that's all the data I collect as a patient every year. No worries. The thing to say to that picture is you might not even see what it is. So you definitely don't see what it is. Introduce myself. My name is Hanna Svensson. I actually don't work for Swelife, but they are the one paying my salary today. I'm a patient representative. In Swedish, I would call myself spetspatient, or lead patient or e-patient in English. I've lived with diabetes type 1 for almost 30 years, and now I've lived with rheumatoid arthritis for approximately 2 years. Ledgångsreumatism. I've also worked in the industry here in telecom and 10 years now. So what I'm doing is combining my experience as a patient and my experience as an algorithm engineer. So it actually started once at Volvo when I was developing one of the first, applying this to my self-care data. It was harder than showing the presentation. So let's talk about, or go to the agenda first. I have 4 bullets I want to talk to you about. What is a patient? Someone just previously said it was someone that just sits quiet. But look for the hashtag "We are not waiting" on Twitter and you will see that's not true. What is care? What is the data we have in self-care? And then I will give you some innovative perspective on this. Patients are a very heterogenic group. No one chooses to be a patient. And when you're asking the question, how is it to be a diabetes patient, or how is it to go to your primary care doctor, or something like that, that's very wrong. Because how it is to be a patient is nothing that the abilities by it. So the patient collections have hit us quite randomly. So in order to create optimal care, you have to take those different personalities and lives in goal into the equation. Because if you don't know what their life goals are, you don't know what to optimize for. Yeah. So being a patient is something all day long. You can go to the next slide. And look at the time here. This is 8,765 hours that I spend in self-care. And 1 hour maybe in healthcare. So that's why the importance of looking into the data that we treat in self-care instead of just looking into a really long, nice presentation about how to structure medical records. And that's important. But we also have to look into how do we get any data at all into the medical records. So when we talk about the AI application should we implement here, we have to think of it as the sum of self-care and healthcare. And it's when we are doing that we can get those good things out of the fancy algorithms that we want to develop. Just go, this is one of the things that are missed on those kind. That's what, and adjust both your medication and what you do. It's a lot about exercise. To exercise, I can switch them by myself instead. It's a lot of exercise. Like one of famous Swedish skier, Robin Bryntesson. He was told when he was diagnosed with diabetes, he was skiing in landslaget, that he should now stop skiing and start walking 1 hour per day. That did not work for him. And it's also about discipline, sticking to what you know works, which is not always so easy. It requires a lot of work. Let's have a comparison about data. When I was diagnosed in 1989 with diabetes type 1, I got a strict diet plan to follow with a carbohydrate content. That was influence my glucose level mostly. I had some limited exercise routines that I could perform, for example, half an hour of walking. And I had a fixed insulin dosage. So it was quite easy to do what the doctors told me. And it was also quite easy to know what I had been doing in the past when they asked me to do skiing in the... And it was not easy to eat out of my regular meal times. Today, you advise your patients to have a free diet. Also about adjust. It's a heavy. They will probably with stating or which is the data of data. I say you of my 2 person who take you ought to answer.